Hello, and welcome to this Edge Computing tutorial. This presentation has been prepared for the 3G, 4G Wireless Resource Centre. I'd like to provide a bit of background about today's session. We're going to talk about definitions of edge computing, how and why edge computing is used, planning for deployment of edge computing, and also forecasts for edge computing. And a little about me too. I'm Jim Morrish. I'm a founding partner of Transforma Insights. We're a firm of industry analysts focusing on the digital transformation space. And a little more background about Transforma Insights. Just one slide in 30 seconds. So we're a new technology research firm. We offer subscription clients a range of assets, including reports, profiles of vendors in the digital transformation space, forecasts, total addressable market forecasts, custom research and consulting, and we also have a database of digital transformation case studies available. And just a very granular level of analysis there, covering all aspects of digital transformation. As you can see on the right-hand side here, that's a bit of an eyeball chart, but you'll see the same thing on our homepage. And on the left-hand side, there's a range of technologies we cover there, including Internet of Things, AI, hyperconnectivity, HMI, data sharing, edge, and so on and so forth, and use cases that are opportunities for vendor and impacting the end user community. So, what is edge computing? Well, it's different things to different people, and the definitions of edge computing vary. A common theme is decentralized processing, or in some way moving processing nearer to an edge asset or an asset out in the field, or a remote asset. There are different perspectives ranging from more centralized to localized. I'm going to talk through those now. So, the most centralized or least distributed perspective on edge is probably that of data center providers, and for these guys, edge is about essentially moving co-location space closer to users, and establishing points of presence in secondary or maybe tertiary cities. Mobile operators would view edge as in the context of mobile edge computing, MEC, which involves the co-location of cloud computing power at the cellular network edge. So that's potentially out at a base station, but actually more often than that, it is deeper inside a mobile network, rather than right out at the base station location. Communications providers, well, it's worth noting here that the term mobile edge computing quickly evolved into multi-access edge computing, with other technology vendors not wanting to miss out on the opportunity, and now it includes a provision for deployment of computing power at the edge of any network, including Wi-Fi and other types of access points. So that's multi-access edge computing. Interestingly, the terminology now is drifting back towards mobile edge computing. So essentially, I regard the two terms, mobile edge computing and multi-access edge computing, both abbreviated to MEC, as essentially interchangeable, and the one that people tend to choose is really changes over time. But it's heading towards mobile edge computing at the moment, as of 2022. Corporate IT departments. For a corporate IT department, edge would essentially relate to processing capabilities that are located at any individual campus location, often co-located with a gateway to wide area connectivity. So that's a factory or some other university campus or a shopping center potentially. It's some edge, some centralized location there, which is distributed away from what we could term the cloud. And then we move down to some more IoT perspectives on edge. So most IoT architects would regard edge in IoT as relating to the piece of IT hardware that is nearest to an OT, i.e. operation technology asset, and that acts as a bridge from the IT world to the OT world, and this definition increasingly extends to include a hierarchy of processing locations, all within a campus environment. So within a smart factory environment, you might have a edge location co-located with the wide area gateway, and then you might have multiple edge processing locations distributed within that campus area, right through to what the software architects would regard as the edge. And for them, the edge is a software container that often resides on dedicated edge hardware, but potentially it can reside on an OT asset or the actual edge device itself. So in the case of maybe a CCTV camera, you might have an edge processing environment actually on the camera itself. So those are some quite different perspectives on edge. So it's always worth checking what perspective somebody is taking when they start describing edge capabilities and what edge applications can do. There is a universal common strand to all of these definitions and all of these perspectives on edge. It's all about bringing intelligence closer to data sources. So edge computing makes processing and storage resources available in close proximity to edge devices or sensors, complementing centralized cloud resources and allowing for analytics close to the origin of the data. The main technical benefits of edge are the ability to support near real-time responsiveness, data analytics at the edge and or end device, and functionality in situations where local devices may not be continually connected to cloud resources, and also device-to-device communication capabilities, so where you have two edge devices communicating directly with each other rather than needing to transit some kind of cloud intermediary. Edge intelligence can potentially allow processing resources to be shared between a number of local devices, with certain devices able to call on processing resources residing in nearby devices. And what that really means is that, and this is quite an advanced concept of edge really, is that a single edge device can look for other edge devices that's nearby, figure out those that have some available processing capacity, and potentially push components of processing onto those devices. That's actually quite a complicated thing to manage, but it is something that is beginning to take off at the moment. So what about the benefits of edge computing? Well, edge computing helps unlock many potential process benefits. Starting on the left-hand side of this slide, one of those main benefits is improved performance. Alerts, analytics, and applications can run faster, close to the originating source of the data. There's no need to send data to the cloud for processing and then receive the results of that processing back again. It's all done, or it can be done locally. There's improved robustness, reliability, and local processing, enabling the autonomous execution of processes, rules, and algorithms, and increased resiliency and uptime due to the elimination of round trips to the data center. And really, both of those things depend on the fact that there can potentially be no wide area connection. So an edge environment can operate in, or potentially can operate in an autonomous way, and will not stop working if a connection to a cloud goes down. There are compliance, privacy, and security benefits. So particularly leveraging local computing based in a specific area, regional domain of a required compliance, privacy, and security boundary. So for instance, something like data sovereignty, you can process data locally using some level of edge computing within a country, and stop having to not have to send that remotely to a cloud or to a cloud location internationally, and at a more granular level, you can process information very close to an individual or to the source of that data, which begins to defend privacy and improves privacy. Of course, transferring data by definition exposes that data to security threats, and storing it in shared data centers does as well. So there's potential security benefits there to edge, and of course protecting privacy by anonymizing and analyzing data close to the source. If you anonymize data before it is sent to a cloud location, then that further helps defend privacy. There is also potential for reduced operational costs, although there's a caveat to this which I'll mention later. So using edge, you can reduce connectivity, data migration, and bandwidth costs associated with sending data to the cloud, because you can process it locally. And this can be significant, particularly in the case of something like a CCTV feed, which is very high bandwidth. And if you can process that locally, you're saving a lot of bandwidth, a lot of data that you might potentially have to send to the cloud. And analyzing and filtering data at the edge reduces communication costs, and also, of course, cloud cloud processing and cloud storage. The caveat to this, though, is that yes, you might be saving those communication costs and cloud processing costs, but processing at the edge or purchasing the infrastructure to process at the edge may well be more expensive than processing in the cloud. So as ever with these things, it's a bit of a balancing act, and it depends on the combination of applications and solutions that you might want to support with edge computing, and you know, there is an optimal solution for many companies pursuing many strategies, but there is very rarely one optimal solution for all companies pursuing multiple different strategies. Multi-access edge computing, or mobile edge computing, as I discussed earlier, is gaining traction, particularly for mobile operators. It's been a work in progress for a while, but it's beginning to gain traction, and particularly Microsoft and AWS are extending their IoT platforms to the mobile edge, which should drive uptake. Several specific application-based IoT platform MEC-enabled projects are in development in the mobile industry, and placing that processing at the network edge can significantly reduce the latency associated with the round trips to cloud services via the core network. This is particularly a consideration in the context of 5G, because the profile of latency in a mobile network has very much changed with 5G. With 4G, most of the latency was in the air interface, and relatively little was in the core network, whereas with 5G it's now possible to configure it so that very little of the latency is in the air interface, and most of the latency is between the edge and the core. And at that point there's obviously far more benefits to moving processing out of the core and towards the edge. It's worth noting as well that MEC has a significant role in supporting mobile private networks. So a mobile private network would be, for instance, a manufacturing location which deploys its own, for instance, 5G cellular network to support their applications within their campus environment. And clearly that is an ideal opportunity to deploy MEC in support of that private network. Data streams and data lakes map to different edge computing locations. So those are two, I guess, fairly familiar concepts, and it's worth just going across that hierarchy across the top of this slide in purple first. So this is the device edge right out near the remote device, edge gateway, enterprise edge, network edge, data center edge, and data center core as you get closer to the core network. So that's the kind of string of edge assets, and all of those might be involved in an IoT solution. There could be an end device, and there could be analytics relating to that device at any level of this edge hierarchy in a way. But it's worth noting that the data stream potentially flows across all of these assets, whilst the data lake tends to sit in the cloud at those more centralized versions of edge computing. So focusing in on that area before we get to cloud, the bit before we get to the data lakes from that previous slide. The campus edge has thick and thin variants based on processor power and suitable for different solutions. So just to unpick that a little bit, not all edge assets are the same. And in a campus context, edge devices can range from small microcontrollers through to powerful enterprise servers. Consequently, there's generally a wide variance of edge asset types within any given campus environment. And here we can see different potential campus edge hardware types, and they're placed on a scale between thin, low compute power edge, and thick or high compute power edge. Clearly these different types of edge assets are better matched to different applications, with the smallest microcontrollers best suited to alarming, whilst resilient operations would depend on all campus edge devices. Compute power is not the only determinant of edge application location, though. For example, relatively unsophisticated access control systems could be supported by enterprise servers within an industrial facility location, so that access to different areas of the campus for individual staff could be most effectively managed with reference to a central database of access privileges. So that's managed at a kind of an edge location which is central to a campus location, even though it's not a particularly sophisticated application, just by nature of the dynamics and the architecture of the data needs and data transmissions to support that application. Clearly, not all applications can be deployed on all edge assets. So, for example, it isn't possible to deploy an AI-enabled video stream processing application onto a small microcontroller. This variety of edge-type devices limits the potential for application deployment, particularly onto industrial machines, although other edge-type assets are essentially IT domain equipment and can be dimensioned to match the task that needs to be undertaken. From this perspective, it's worth calling out the edge gateway, which can potentially be co-located with an industrial machine. Unless an industrial machine has been designed specifically to support higher level edge computing or can be upgraded with more onboard processing power, then the edge gateway represents the closest that high-powered compute infrastructure can be located to an industrial machine. For many older industrial machines, then, the deployment of an edge gateway co-located with the industrial machine represents something of an optimal solution. To get the edge computing any closer to the machine, i.e. onboard the machine, would involve a substantial upgrade or replacement, while the deployment of an edge gateway can offer a very substantial processing power in close proximity and directly connected to the machine in question. Essentially, an edge gateway can often be the most effective way to get the maximum amount of information from an industrial machine without having to significantly upgrade that machine. As a result of these limitations that I've just discussed on this slide, the on-campus edge infrastructure can become a relatively complex and diverse place with a range of different device types with different processing power available at different locations and varying requirements as to the optimal location of different edge applications need to be considered against this potentially complex landscape. And clearly, of course, data architectures are becoming significantly more complicated as well, given what we discussed in the last couple of slides about some of the topology of the networks and the way that multiple levels can be involved in an application, and also the diversity of assets that might feature particularly out in a campus environment. There's a lot going on in this space, or there can be when you start to develop solutions for it. So the next thing to do is to consider the dynamics of information or data as it flows over edge assets. Currently, organizations will often establish their analytic approaches and frameworks at central cloud locations. However, as discussed earlier, there can be significant benefits to undertaking certain analyses closer to the end device. A specific example might be the case of AI-enabled analyses of machine status information, where powerful cloud infrastructure can be used to establish rules to support, for example, preemptive maintenance alerts. And then any rules identified can be deployed locally and updated dynamically. The resulting benefits would likely include a reduction in data sent to the cloud for processing and more responsive and resilient local monitoring capabilities. So the first dynamic associated with the advent of edge computing is a trend to push decisions closer to the edge. Conversely, raw information originating from an edge device can be redacted, by that I mean filtered or aggregated, as it flows over edge infrastructure, ensuring that only necessary and meaningful information remains for onward transmission. In the example above, once preemptive analytics have been deployed locally, it simply isn't necessary for the same raw data to be transmitted onwards to cloud infrastructure, and a digested form could be sent instead to accelerate the central analytics that reside in the cloud. Lastly, information flowing from edge devices can be augmented as it flows across the various edge assets by associating contextual and other information, often including information from other local devices. For instance, in a machine monitoring example, as just described, the machine may have onboard sensors to monitor operating temperatures, and computers located at the device edge or edge gateway level could be well placed to identify increasing device temperature if that's the result of some kind of malfunction. However, relevant contextual information might be that factory air conditioning systems have failed, and thus it's likely that increasing device temperatures are simply a product of reduced cooling input. The potential for this kind of data augmentation increases with effectively distance from the end asset. For instance, the enterprise edge is a good location from which to analyze and control an entire local facility, including buildings and building condition, the performance of any manufacturing lines, and organization of work within that facility. In general, then, the volumes of data tends to reduce as they travel away from an end asset, but the information that remains is generally richer and more meaningful. And it's worth just touching on some of the trends that are ongoing in the market at the moment and the focus of the market right now. There's a lot of focus on the device edge and on edge gateways, and also network edge, and to a slightly lesser extent enterprise edge. There's less of a focus on the data center edges than the data center cores, that cloud infrastructure. That's better developed infrastructure. There will be evolutions in that, but the focus at the moment is basically on the campus located assets supporting edge, and potentially including network edge and mobile network edge. Focusing again on the campus, data ops is a fast emerging concept in the edge domain. So to explain a little more, what data ops can do is it allows for the optimization of data flows and the location of application deployment within a local campus environment, including deployment to and federated support of devices with limited onboard processing. Data ops at the edge might include configurable application-specific synchronization policies between cloud and edge, and within the on-campus edge, and data partitioning so that only the business data needed at a specific edge location is distributed and synchronized. This approach effectively renders all available compute processing assets within a campus as a single managed distributed computing environment, and has the potential to more effectively support a range of edge type applications, including, for example, in the case of a manufacturing facility, and I'm going to run through some examples from the edge towards more aggregated levels as I go through here. So at the most detailed, the most remote level of edge, onboard processing for monitoring and controlling the performance of an industrial robot, for example. And then a next level up, there are device gateways for interworking between the data feeds from a production line machine and control messaging, including protocol translation that might be needed. Production line management can be undertaken at the level of a single production line, potentially including video-based and AI-enabled quality control. And then moving up a level again, multiple production processes could be managed together to support synchronization between different processes, for example, manufacturing, packing, and parts delivery, and then at a central enterprise edge infrastructure location, which could be an appropriate point from which to manage overall production at a manufacturing facility, taking into account production deadlines, stock levels of component parts, and supply chain information. So you can see there that there can be different types of application which naturally sit at different levels within this kind of distributed campus environment, and the trick is to manage the location of the applications and the flows of data required to support those applications in an effective way. The general principles underlying this kind of distribution of applications within a campus edge environment are that application functionality that is either mission critical or time critical or relies on high data volumes should be deployed as close to the relevant sources of data as possible, meanwhile recognizing the potential to increase the scope of an application in terms of the variety of data that it can ingest from different sources as it moves further away from that edge data source. And as I've alluded to a few times through this presentation, enterprise edge is something of a sweet spot which can combine a number of benefits. I'm going to run through those. Firstly, compute power. Significant compute power can be easily available at the enterprise edge at reasonable cost. Compute power deployed at the enterprise edge is also generally scalable, and additional compute power and storage can be added relatively easily. There's still low latency this is still the enterprise edge is still a local version of edge, or a very local version of edge. So analytics at the enterprise edge benefit from high-speed local network connectivity within local facilities, and also avoid the need to communicate information to cloud locations. Data redaction. Since local data transmission is essentially free within most facilities, there is often limited benefit in redacting data any nearer to end devices than the enterprise edge, whilst redacting at the enterprise edge can potentially save significant costs associated with transmitting data to the cloud and processing data using cloud infrastructure. It's quite optimal for data augmentation as well. So it's an ideal location to draw together all kinds of data streams from within a local facility, ranging from machine performance information to building information and more. It is also an optimal local location to draw in any useful information from remote cloud locations, including information like weather forecasts or supply chain status information. And in terms of security and privacy, information at the enterprise edge remains in locations controlled by the operators of a local campus environment, so eliminating some aspects of security and privacy risk. In particular, storing data at the enterprise edge can make it easier to demonstrate compliance with certain data sovereignty requirements. So overall, these factors make the enterprise edge an ideal location for undertaking all kinds of analyses of the wide range of information generated by a local facility. There's also a particular synergy with the advent of 5G private networks, since 5G networks can support very low latency communications, and MEC can provide an efficient bridge between the private network and compute power deployed at the enterprise edge. Although arguably increasing other aspects of security and privacy risk, for instance those aspects of risk associated with physical access to servers, the balance of security risks will change from scenario to scenario. There are many potential use cases for edge computing. Only the most compelling are listed on this slide, but some of the particularly compelling use cases include redaction at the edge. I've mentioned multiple times through this presentation, which devolves processing to an edge device in order to reduce bandwidth requirements for cloud connectivity, and commonplace applications you include such as AI-enabled CCTV, which relies on scanning live CCTVs for certain behaviors or events, and that's done locally, and only the results of those analytics are then communicated to the cloud, or potentially snips of video as required to support those conclusions and observations, not the whole stream. AR and VR. And in the case of AR and VR, a real-time experience is often key, requiring very low latencies, and these applications basically have to interwork real world and digital world seamlessly, and placing processing power near to the end user allows for far greater responsiveness compared to cloud-based solutions. Edge is particularly relevant in the case of artificial intelligence as well. So a typical model for AI involves transmitting a large volume of information to cloud servers for analysis and for the determination of business rules, which are then deployed or devolved out to edge devices. This approach allows AI solutions to benefit from both cheap processing in the cloud and the rapid response times and bandwidth efficiency associated with the edge. And another particularly beneficial use case is that of autonomous operation, where edge devices can potentially work independently of any connection to cloud infrastructure. And this allows for the deployment of digital transformation solutions into environments where connectivity quality cannot be guaranteed, and local caching of information further extends the potential for autonomous operation. So those are some of the really key use cases that are supported by edge today. Markets for edge computing are evolving quickly, with standardization and servitization, or XaaS, propositions emerging. So just looking at some of the evolving aspects of edge computing, starting on the left, standardization. The IoT edge, in fact many edge environments, they're not yet standardized, but standardization is coming. The benefits will be reduced vendor lock-in, increased application portability, and the potential to run applications from different vendors on the same hardware more efficiently. MEC deployments of IoT platforms. This is quite an impactful development, and as I mentioned earlier, AWS and Microsoft particularly are partnering with Verizon and AT&T respectively, and also AWS is collaborating with Vodafone, SK Telecom, and KDDI to support Edge in collaboration with mobile networks. And effectively, that allows a mobile network to offer an edge processing environment, which is almost edge as a service. Which is another, in fact, of the key developments. So the development of IoT platform capabilities, the network edge, basically MEC and some other things, as described earlier in terms of those data ops considerations, are effectively taking edge in the direction of edge as a service. There are going to be very significant synergies, as I've mentioned earlier, with 4G and 5G private network deployments. And it's a significant enabler for AR and VR solution, as mentioned on the previous slide. Solutions will likely emerge related to asset monitoring as well. So Edge as a service is quite an important development. And I've mentioned MEC in 4 and 5G private networks a few times. It's worth just highlighting there that there is a particular benefit in the case of the ultra reliable low latency communications aspect of 5G private networking, which can support very low latency communications, and that is particularly synergistic with deploying processing out to an edge environment in terms of getting a near real-time response in terms of data analytics to ingested data. And the combination of these things is a particularly good way to bring IoT capabilities to industrial locations. You have IoT platforms, you have private networks, you have MEC, and together that's quite a compelling platform on which to deploy IoT capabilities in industrial locations. Any planning for edge computing deployment, particularly in a campus environment, must take into account that edge computing is a wide-ranging and long-term concept. And by what I mean by that is it's not just something that will be deployed to support a single application. It's something, edge computing environment is something that will become a common asset, and it's shared, and it will support multiple solutions over a long term. And the edge computing over an environment overall within a campus location will have probably a longer lifetime than any of the applications that it supports. So it's worth thinking ahead a little before just deploying an edge computing environment. So the first thing to do is to understand the potential. Typically an edge deployment is considered to support a specific application, but there could be many other applications that could benefit from edge technologies. So for example, AI-based applications and solutions that involve the control of multiple devices. So an end user should understand what the full potential of edge is in their business before embarking on deployment. And related to that, plan ahead. Standards are not yet widespread adopted in edge markets, so end users need to consider which vendors to partner with and how that mix will evolve as more edge services are needed, and also consider the vendor's approach to standardization and development path, since a commitment to convergence to relevant standards is crucial. And also consider the context. In early stages of edge adoption, end users will not have many edge applications. Basic edge solutions and services are fairly simple. It's therefore tempting to adopt edge capabilities incrementally. But platform-enabled and edge as service propositions can bring flexibility. And the question is the wider business likely to benefit from these aspects, and to what extent would deploying a servitized or an as-a-service proposition or a platform-enabled proposition simplify the long-term maintenance of that edge environment? I want to talk a little about some forecasts for edge adoption now, and we think that edge computing divides into two main groups of devices, totaling about 7.8 billion devices. There's the edge-enabled devices, which include IoT-connected devices that have edge computing capabilities, and they account for the vast majority of the device count. They're in orange on the chart on the left. There's also campus edge, including edge gateways and distributed generic edge devices in campus locations such as smart factories, and that's the little green sliver you can see on top of the orange on the left hand side. Now you'll notice here that obviously the vast majority of edge devices by count are the edge enabled devices. Meanwhile, much of the presentation I've been focusing on campus edge, and this is one of the oddities about the edge space. The count of devices is driven, as we'll see in a few slides, by some fairly standardized products which get distributed to particularly consumer markets. Whereas the digital transformation potential that is unleashed by edge is very much characterized by complex deployments in complex environments, in campus environments. So in many ways, that this chart is showing two things. One is a device count of products, and the other one is a series of assets underpinning digital transformation in enterprise environments. And I'll unpick that a little more in the next few slides. Focusing first on the IoT side, so that larger of the two categories on the previous slide, around about 30% of all IoT devices will be edge enabled, and by that we mean have some significant onboard computing power. The largest markets for edge-enabled devices are Greater China, Europe, and North America. There's an uptick in the edge-enabled share of IoT devices in 2021, and that was driven by increased sales of connected televisions during COVID-related lockdowns. And in later years and beyond 2030, the edge-enabled share of IoT devices falls due to an increasing number of simple sensing IoT devices, particularly supported by LPWA technologies. So those pick up a little later in the forecast period, and there's a lot of those particularly simple sensor devices supported by LPWA technologies in the medium term. That pulls the percentage down of IoT devices that are edge enabled. Just focusing on the edge enabled devices for a moment, you'll see that firstly from these two charts, on the left we've got consumer markets, on the right hand side we've got enterprise markets, and this is edge enabled IoT devices. Firstly, you'll see that the consumer numbers are far bigger than the enterprise numbers, so the consumer numbers get to approaching 7 billion by 2030, whereas the enterprise numbers are more like 1.2 billion. And that reflects one of the core dynamics of IoT when you start looking at device counts, which is that the size of the addressable market tends to be very dominant, and for instance in this case things like consumer internet and media devices, those are things that could be potentially sold to every individual on the planet. So there's 7 or so billion of people who could buy a edge-enabled television, for example, and that effect tends to result in edge markets being dominated by consumer products, and you'll see there's a lot of concentration in the distribution curve on the green on the left hand side. Consumer internet media devices, that's set-top boxes and stereo equipment and smart speakers and televisions and so on. That makes up the vast majority of edge enabled devices. Connected to vehicles is another significant chunk, but after that it's quite a long tail of things like security and fire alarms and real-world visualization, that's AR and VR glasses, and some office equipment like printers and so on in a domestic environment, and building automation. Whereas on the right-hand side, you'll see that a much more diverse combination of edge-enabled devices in the enterprise context. So connected vehicles is the most numerous asset type that is edge enabled in enterprise context. CCTV, again, consumer internet media devices, because there are televisions in enterprise contexts as well, but obviously far fewer. Remote process control is a significant contributor to the count of edge-enabled devices. Inventory management and monitoring, security and fire systems, payment terminals, building automation, precision specialist robots, and so on. And many of these things which are edge-enabled IoT applications, for want of a better word, that they will or could potentially be stitched into campus type solutions. So just looking at this list on the right hand side, there's CCTV, there's remote process control, there's inventory management and monitoring, security and fire alarms, building automation, precision specialist robots. All of those things could be stitched into a smart factory style solution, which takes us very quickly back to the campus edge considerations that we've been discussing a few slides back, and where all that complexity resides in terms of pushing the applications out from the cloud towards local environments and redacting data as it heads across the network, and augmenting it again as it heads toward the cloud. So some really much more complicated and fragmented considerations on the enterprise side than on the consumer side with edge. And just to summarize, the opportunities for end users adopting edge computing are very significant, whilst risks relate to vendor lock-in. So just going through some of those opportunities. Edge computing unlocks significant new opportunities. So many digital transformation solutions would be essentially unable to operate without edge. Examples include AR, VR, and self-driving cars. Edge can significantly increase the functionality and performance of many more applications. Examples include AI and smart CCTV applications, and also Edge can facilitate compliance with rules and regulations around privacy and data sovereignty. So there's many strong things and many benefits to deploying Edge. There are, however, some risks, and the risks relate to standardization and flexibility. So the Edge environment is not yet standardized, and so edge applications may not be portable between different vendor devices, and it's key to avoid lock-in to a vendor that does not have a robust strategy for standardization. And also deploying processing at the edge can potentially limit future flexibility to refine and enhance operations. The more data that gets communicated to the cloud and stored, the more that can potentially be done with it. And that's the flip side to the data redaction benefit that I was talking about earlier. It may save on bandwidth transmission, and it may save on round trip delays and real-time analytics to process data streams locally. But if you do process them locally and you redact the data and you just effectively don't store it at all, other than the conclusions of any analytics, you don't then have that data to fall back on at some future point if you want to start doing historic analyses. So you've got to be careful about what you dispose of. So I hope you enjoyed that presentation on edge computing and found it interesting and informative. I'm Jim Morrish. I'm from Transforma Insights. If you'd like to find out more about Transforma Insights or edge computing from the assets on our site, or indeed assets and information about other digital transformation technologies, please feel free to surf over to our website. There is an option to get free access to some of our reports and publications, and what you would need to do is click the subscribe button with a orange arrow to it there, and select an essential plan, which is free, and you would then be able to pick one vertical and 2 technologies, and that will give you access to our case study database for a specific vertical and case studies including 2 sample technologies, just as a free view of 2 cells in that matrix effectively. So do that and you will have access to a range of resources on our website, and please feel free to get in touch with any questions.